In this problem, we are given the following op amp here, and we are told that it is ideal. We are also given that our V of G is equal to 2, this is our V max, and then the cosine of 100,000 T volts. And we need to find the steady state output, and also we need to see how large the amplitude of our VG can be before our amplifier saturates. And we know that saturation happens at this point or this point. The 5 volts is the max and the -5 is our minimum. Remember that it is linear when an op amp operates, with a -5 at the bottom and our 5 at the top. So to solve this, we are going to use a node voltage analysis. From what I've seen, it's usually how you solve this. We're going to have our Vn here. We're also going to have our Vp here, Vn for negative and Vp for positive. And we know that our Vn is equal to our Vp, so we're going to set these equal to each other. And now we can solve this. So we know we have some voltage going this way, and we're going to have some voltage going this way. However, there's going to be voltage split across this and across this. So it's going to be across the capacitor and the resistor. Both are impedances, and we're going to have to factor that in. When we're looking at our Vp, we know that we have some voltage going this way. We also know that we have some voltage going down this way. Now we can start writing our equations. First, I'm going to start with the Vn, and we know that our Vn is going to start over our 160 kilo ohm resistor. Next, we're going to have our Vn minus the V0, and this is going to be happening over our capacitor. Well, we need to convert this into our XC form. We can't just have it as the nanofarads. So to convert this, we are going to use the formula that can be found in the notes linked below the like button. And this formula is that our X of C is equal to a -J over our omega times C. And we know that our omega is given to us as 100,000. This is the omega for the formula. And this is being multiplied by our capacitance, which is 0.1 nanofarads, or 0.1 times 10 to the -9, because that's what a nano is. And if we do this, we are going to get -100,000. We can also write this instead as -100 times 10 to the cubed. Or we can say that this is 100k for kilo, and since this is an impedance, it's going to be in ohms. And lastly, we are going to have our J in here. We cannot forget our J, otherwise it's going to mess up the entire problem. So this is going to be over our negative, and I'll put the J out front, 100 times the kilo ohms as units. Next, we have the voltage over the 200 kilo ohm resistor, so we're going to have a plus. We know this is going to be our Vn minus our V0, and again this is divided by 200 kilo ohms of resistance, all set equal to 0 per the node voltage method. Now when we look at this, I want to simplify a couple of things just to make things easier. I'm going to get rid of a 0 in the kilo ohms for each of these. Once I do this, I am going to multiply everything by 80 just to get rid of the denominator, and that's going to be our equation. Now we can start adding things together. First, I'm going to add our Vn's, so we're going to have a 9Vn minus our 4V0. Now we're going to have to deal with this. If we want the J in the numerator to flip it up, we are going to have a -J. So we're going to have a plus J with our 8Vn, and then we're going to have a -J with our 8V0, and this is all equal to 0. Now we can combine our Vn's, factoring them out, so we're going to look at this Vn and this Vn first. We are going to have the Vn, and then inside of it we will have our 9 plus J8, and then we are going to have our V0s right here. So we will have a plus V0, and then inside of here we are going to have a -4 minus J8, and this is set equal to 0. We know that our Vn is equal to our Vp, so instead of writing Vp for this part, I'm just going to write Vn, but they mean the same thing. In solving this, we are going to have our Vn minus our Vg, and we know that our Vg from this is going to be 2 with the angle of 0 degrees, because there's no angle in here. So again, we have Vn minus 2 with our 0 degrees angle here, and this is going to be over the 20 kilo ohm resistor. Again, we're looking at this part right here now to solve for our Vn. And then we're going to have a plus with our Vn over the 80 ohm resistor, 80 kilo ohm resistor, and this is all set equal to 0. Now I'm going to simplify this. To do that, I am going to surround this. I'm also going to get rid of the 0 kiloohms here, and then multiply everything by 8. I also converted this part, which is the polar form, into our rectangular form here. To convert from polar to rectangular, we are going to have the number, which in this case is the -2 out front, and then in parentheses we're going to have cosine of our angle plus j times the sine of our angle, and then this is all in parentheses. And for this problem it's going to give us a -16. I did make a mistake here. I just realized that this should not be 16, instead this should be 8. And that's because when we convert this, we are going to have a 2 plus 0j, or I'm sorry, -2 plus 0j. And then we have this 8 right here. However, we're not multiplying by 8 because remember it cancels out with this a little bit, so we're actually multiplying by 4. So we have -2 plus j0 times 4, and so that'll be a -8. That means instead of a 16 here, we are going to have an 8 here. And that means when we divide this, we're going to get that our Vn is equal to 1.6. And this is going to be our Vn value. And now we can substitute this back into this equation here and then factor it in. When we factor this in, we're going to have 1.6 times 9 and then 1.6 times j times 8. And this is going to give us a plus j with our 12.8. And then we have a plus v0 with the rest of the stuff inside of it. And to solve for this, remember because it's set equal to 0, we are going to subtract these from both sides, and then we're going to divide this part. And then we're going to get that our v0 is equal to -14.4 minus j times 12.8. And this is all happening over the -4 minus j8. Now we need to plug this into the polar equations to find the polar form for this, because currently it's in rectangular form. To find the polar form, we know that we can use that our v0 is equal to the square root of our real number squared plus the imaginary number squared, and then we're going to get that our theta is equal to the tangent -1 of the imaginary number over our real number. And that's going to give us approximately 19.27 with the angle of 41.6 in the numerator, and then 8.9 with 63.4 in the denominator. However, we do have a slight problem. We can see here that we have two negative numbers. So if we plot this on our graph, I'll do this right here, we are going to have our x on the x-axis and our I in the y-axis for imaginary number. We can see for both of these that our x is negative and our I is negative. So it's going to be somewhere in the third quadrant. However, when we find our angles right here, they're both positive, meaning that they're in the first quadrant. So that means we're going to have to add 180 degrees to both of these to actually find the correct answer. So that means our real V0 is still going to be equal to 19.27 over 8.9. However, our angles are just going to be 41.6 plus 180 and then 63.4 plus 180. From this, we're going to get approximately 222 degrees and then 234 degrees. And from this, with the real numbers, we're going to divide them, and with our angles, we are just going to subtract the bottom from the top. From this, we're going to get that our V0 is equal to approximately 2.152. There's a little bit of rounding error here, but that's the correct answer. From this, I got 2.165, however, both should be correct. And then for the angle, I got negative 21.8. And now we can write this as our answer for part A. We're going to have 2.152 in here, and then just a negative 21.8. If we did not add 180 to both of these, we would have a 21.8. So if we just solved for how it was right here, we would have 21.8, and we would be about 180 degrees off. So remember, it's always important to check this part and make sure the angles are in the correct quadrant. Now we are going to solve for our part B. We want to find V0 max, and we know our V0. And this V0 is the answer for part A. We are going to say that our V0 is equal to, and then we are going to use the polar form for this, which is 2.152 with our angle of negative 21.8. And saturation is at this value, 5 and negative 5V. However, we can't just find our I max here. we know that our 5 volts and our negative 5 volts is going to go into here. So we need another kind of value to compare this to. Well, what we can do is, since this is steady state, is use our VGT. We're going to have our V0 over our VG, and this will be equal to the division of 2, and we have our 0 angle right here. So this is also the polar form. Now we're going to divide these out, and we're also going to substitute our 5 volts in here. We'll put a plus minus 5 volts because we don't know exactly which one is greater. And remember, for the numbers we are dividing, and then for the angles we are subtracting the bottom from the top. And after we do this, we are going to get 1.076 with the angle of negative 21.8. Now we want to find our V of G, so we're going to multiply both sides by V of G and then divide both sides by everything that's on the right. And then we are also going to convert this 5, because currently it's in rectangular form, to our polar form. And now we have these values. And our V of G is going to be equal to our V0 max, because our VGT is equivalent to our V0 max. That's what we're saying when we put it in this kind of equation right here. So we are going to do the same thing where we divide these out. Again, remember that the real numbers right here, we are dividing them, and our degrees, we are subtracting them. So we're going to have a plus minus 5 divided by our 1.076. And this is going to give us a plus minus, and this is going to give us approximately plus minus 4.65 with an angle of 21.8 degrees. And this is equal to our V of G. Now, for our voltage, we don't really need to worry about our angle right here. It's not important to our overall problem. And in fact, we know that if we were to, since it's in the polar form right now, convert this to the rectangular form and then convert it back to the polar form, we would get that our V of M is equal to 4.65. This is the form for it. Our V of M is the first number and our theta is the second number, and we want only the V of M. So this 4.65 right here is going to be the answer to our problem, and it's going to be a plus 4.65 on it, obviously. And the lower part, if we did have another lower part, it would be a negative 4.65. And that's how you would go about solving this problem. If you have any questions about this problem, you can leave them in the comments below. If you want more introduction to circuit analysis or notes covering the entire coursework for this subject, you can find them in the description below the like button.